the sheet. Although you know the sheet has problems, most of which you can handle with stuff that I taught in the last class. But nevertheless, let me add some more things which we would require to make our understanding of definite integrals reasonably complete. Okay. Now, look at the graph of a function y equal to fx. From x equal to a to x equal to b. This interval, which is of length b minus a units, this interval along the x-axis, which is of length b minus a units, I break it up into n equal intervals of h units. I break it up into n intervals of h units each. That means b minus a is nh. N intervals, each of length h units. Each of length h units. Now, so if the first one is x equal to a, the second node is going to be a plus h. This is going to be a plus h. The corresponding, see, the ordinate at a is going to be fa. The ordinate at a plus h is going to be f of a plus h. The ordinate, the next ordinate is going to be a plus 2h. I'm sorry, the x coordinate. The ordinate here is going to be f of a plus 2h, and so on and so forth, going this way. B is a plus nh. B will be a plus nh. So the one just before B would be h units less. This is going to be a plus n minus 1 into h. The ordinate here is going to be f of a plus n minus 1 into h. Now, although, let me also put a disclaimer here. Whatever I am doing, even though I am breaking this interval from x equal to a to x equal to b into n equal parts, I am not obliged to do this. So bear this general interface in mind. It's my choice as to how I want to break this length b minus a into a certain number of units, whether equal or unequal. But in this case, for convenience, I break it up into n equal units, n equal lengths, h units each. Right? Now, this entire thing then, say this is a rectangle. This is a rectangle, right? This rectangle, the shaded area that you see, this length is f of a and this length is h. What is the area of the shaded region therefore? F of a into h. Right? F of a into h, right? Then look at the next rectangle. This rectangle. This rectangle. This ordinate that you witness here is f of a plus h into h, right? So the area of the second rectangle that you see here is going to be h into f of a plus h. Similarly, the next one that you will see here, this rectangle, this would be f of a plus 2h into h, right? Going this way. up to the last one, which is this. F of a plus n minus 1 into h into h. Now, this could be looked upon as approximately the area under the curve. This is an approximation to the area under the curve. Do you realize that? What's the error in this area calculation? The error are these small upper regions. You know, these small upper regions that you see here? That's the error in the area calculated, right? This is an approximation to the area under the curve y equal to fx. But in this calculation, there is an error. There is an error. What's the error? The error is some of these areas that you see in the top region. Some of these areas that you see in the top region is the error in the area calculations, right? Now, so essentially, you know, this summation h into f of a plus rh r equal to 0 to n minus 1 is a decent approximation to this area, is a decent approximation to this area. Right? Area under the graph of y equal to fx. Now, the error, like I said, would be some of these areas. Some of these areas would be the error produced, right? Now, as h becomes smaller and smaller, as h becomes smaller and smaller, each of these will become smaller and smaller. Therefore, the error will decrease. The error will decrease as h becomes smaller and smaller. That means as the number of divisions increase, that means the size of each unit decreases, the width of each unit, each of these rectangles decreases. Then the error obtained out of this calculation will decrease, right? As h tends to 0, the error in the area will tend to 0. And you get the exact area under the graph, right? Which means, if I did a limit of this summation as h tends to 0, summation h into f of a plus rh r equal to 0 to n minus 1, if I did this limit as h tends to 0, then what I get is the exact area under the curve. What I get is the exact area under the curve. Yes or no? Right? And this area will see, integration is essentially a process of summation of this kind. That means this would be given by, this actually gives us integral fx dx. X runs from a to b. Actually, the meaning of integral fx dx from a to b is this limit, That's the meaning of this integral fx dx from a to b. It symbolizes this summation. Right? It's summation of how many terms? Infinite number of terms. Why? Because as h tends to 0, see, the number of terms here are n. As h tends to 0, n will tend to infinity. Why? Because h is b minus a, n is b minus a by h. Right? So as h tends to 0, n tends to infinity. That means the number of terms in this summation will become infinitely large. Right? So this is integration as a limit of a sum. This is limit of a sum of infinite number of terms. Yes or no? Right? Now, clear? just to give it different algebraic looks, right? So what we have is integral a to b fx dx is limit h tends to 0 summation h f of a plus rh r equal to 0 to n minus 1 is what we have, right? So writing everything in terms of n as h tends to 0, n tends to infinity. So let me make n my new subject, n tends to infinity, summation b minus a by n, right? H is b minus a by n, r equal to 0 to n minus 1. Can I just remove this and create room? Right? Now what this, a special case of this is very commonly used in evaluating limits. See, till this point we have evaluated limits one way, but one thing, if someone didn't give you this but gave you this, and this evaluating this limit could become very cumbersome, could become very difficult. But then if it is in this form, realize that it could be reduced to this definite integral, which would be lot easier to evaluate, right? So we don't go from here to here because that's making it complicated, but we actually go from here to there. We go from here to there, right? And therefore a special case of this which becomes very, very useful, is the following. The case where the lower limit is 0, a is 0 and b is 1. A is 0, b is 1. A is 0, b is 1. Which is very effective a tool in evaluating limits of a certain kind. I'll tell you what kind. N tending to infinity, summation 1 by n f r by n r equal to 0 to n minus 1. This n of course is independent of r, so it could scoop out of the summation sign if you so desire. This could be looked upon as limit n tending to infinity 1 by n summation f of r by n r equal to 0 to n minus 1. Now one thing let me tell you, whether it's 0 to n minus 1 or 1 to n or 0 to n or 1 to n minus 1, it will not make a difference, because infinite number of terms, a term more or a term less will not change the limit. It will not make any difference. Now so sometimes you might just have 1 to n, then also it will reduce to integral fx dx 0 to 1. Sometimes you might have 1 to n minus 1, then also it will reduce to this. Now let me tell you a rule that will help you evaluate these limits. Given something like this, how do you reduce it to an integral? How do you reduce it to a definite integral? Think of it like this, as n tends to infinity, 1 by n would tend to 0. So 1 by n is like a dx, which is very, very small, infinitesimally small, right? So the 1 by n that you see here should be replaced by a dx. So replace 1 by n by dx. So dx, right? Summation represents integration, right? So the summation, integration. And replace the r by n by x, fx. Replace the r by n by x. So f of x. Now, the lower and upper limits of integral. How do you evaluate the lower and upper limits of now? Look at the lower limit of the summation and look at the upper limit of the summation. Right? The lower limit of the summation in this case is summation here is, in this case, is 0, but it need not always be 0. It could be 5 also. It could also be in terms of n. These lower and upper limits also could be in terms of n. This could be n squared and this could be n cubed, for example. That's also possible, right? You know what I'm saying? The lower and upper limits, or one could be some alpha as a function of n, this could be some beta as a function of n. Say the lower limit of the summation is alpha n, Say the lower limit of the summation is alpha n. Then the lower limit of the integral a, is going to be given by a limit alpha as a function of n divided by n as n tends to infinity. That will give you the lower limit of the definite integral. Look at the lower limit of the summation. In a very general sense, it could itself be a function of n. It could itself be a function of n, alpha a function of n divided by n as n tends to infinity. That will give you the lower limit of the definite integral that it represents. Right? You know what I'm saying? B, the upper limit. So if the upper limit of the summation, see in this case alpha is 0. So this will simply become 0 by n, which is 0, and as n tends to infinity, 0 tends to 0. So that's why in this case it turns out to be 0. But it need not always be a constant like r equal to 0. It could be something else, right? It could be some function of n, right? That will determine the lower limit of the definite integral. Now if the upper limit of the summation says beta n, is beta n in a very general sense a function of n. In this case it's n minus 1. Sometimes it could be 2n, it could be 3n, right? It could be 4n, whatever. It could be some function of n. Then if the upper limit of the summation is beta n, then the upper limit of the integral is going to be given by a limit beta n by n as n tends to infinity. In this case, beta n is n minus 1. Limit n minus 1 by n as n tends to infinity is limit 1 minus 1 by n as n tends to infinity, which is 1 in this case. That's why you have this as 1. But what I have done is I have actually given you a generalization. It need not always be like 0 to n minus 1 or 1 to n minus 1 or 1 to n. It could be something else also. So if the lower limit is a function of n, alpha a function of n, divide that by n as n tends to infinity, that will give you the lower limit of the definite integral. If the upper limit of the summation is beta a function of n, then beta n divided by n as n tends to infinity will give you the upper limit of this integral. Remember this. Right? Now, just to illustrate some of this, look at the sheet in which the problems titled 6, 1, 2, 3 belong to the required category. Let me just give you a hang of things here. So 1 by n to be replaced by dx, r by n to be replaced by x, summation to be replaced by the integral sign, alpha n by n as n tends to infinity will give you the lower limit of the definite integral, beta n by n that will give you the upper limit of the integral, definite integral, and so on and so forth, right? So these are the rules that you must bear in mind. The first one, limit n tending to infinity, 1 by 1 plus n plus 1 by 2 plus n going up to 1 by n plus n. Right? Let's see what this turns out to be. This is n tending to infinity, summation 1 by r plus n, r equal to 1 to n, r equal to 1 to n. Now, I need a 1 by n outside. If at all I have to reduce it to a definite integral, I need a 1 by n outside, so I force a 1 by n out of it. So, limit n tending to infinity. I took 1 by n common, so 1 by n can come out of the summation sign also because it's independent of r. Right? So, 1 plus r by n, r equal to 1 to n. Right? Now it's exactly the format that we want. Limit n tending to infinity 1 by n, and this is a function of r by n, f of r by n. It's a function of r by n, right? It will reduce to integral. Now, this summation to be replaced by this integral sign, 1 by n to be replaced by dx, f of r by n to be replaced by x, and 1 by n as n tends to infinity is 0, so the lower limit will be 0. N by n as n tends to infinity would be 1, so the upper limit would be 1. Nahi kya? Are you confused? No, na? So this simply becomes log 2, isn't it? Try evaluating this limit without the aid of this. From the tools that you have learnt in the past, you'll get bamboozled. Right? There is merit, therefore, in this. Right? And you know, someone might say, all right, as n tends to infinity, see, I'll tell you the faulty thinking that could prevail sometimes. Just to ward you off that faulty thinking, one say as n tends to infinity, well, this tends to 1, this tends to 0, this tends to 0, this tends to 0, this tends to 0. So 0 plus 0 plus 0 plus 0 plus 0 plus 0, 0, 0, 0, 0 all the way. No, no, no. You know what's wrong with that thinking? Limit of a sum will be sum of the limits only if the number of terms are finite. You can't apply that rule to infinite number of terms. Limit of a sum will be sum of the limits only if there are finite terms. Therefore, you cannot apply that. Now, let me also illustrate the next one belonging to the same category, problem 2. Limit n tending to infinity, n plus 1 by n squared plus 1 squared, n plus 2 divided by n squared plus 2 squared, 3 divided by 5n as n tends to infinity. Now, to begin with, you know, it might seem odd because these seem like belonging to the same family, and this one seems like an odd man out. But maybe not. See, this I could write as limit n tending to infinity, n plus 1 by n squared plus 1 squared, n plus 2 divided by n squared plus 2 squared. Now, if I have a 3 here, maybe it's like a n plus 2n. Giving me a 3n. Maybe. Let's try that out, right? That's a way I can get a 3 in the numerator. So n plus 2n, and then n plus 2n, n squared plus 2n whole squared. See if it falls in place. Isn't it? Now it's a 3 by n. Good. Isn't it? It fits the bill. Now this is limit n tending to infinity. You realize what prompted me to write this as n plus 2n? And therefore check with the denominator in the same form, right? So n tending to infinity summation n plus r by n squared plus r squared, isn't it? Where r runs from 1 to 2n, yes or no? R runs from 1 to 2n? Let me see if it will fall in the category discussed. I have to take a 1 by n common from the summation sign first. I take n common from this and n square common from this, then I'll have a 1 by n in the denominator, right? So I take n common from the numerator, n squared common from the denominator, then I have 1 plus r by n, 1 plus r by n whole square. R equal to 1 to n. R equal to 1 to 2n. N tends to infinity. Clear? Right? Now, 1 by n summation f of r by n. All's good, right? 1 by n could be replaced by dx. R by n could be replaced by x. Summation could be replaced by an integral sign. So, summation 1 plus x by 1 plus x squared dx. Right? R by n to be now the lower and upper limits of integration here. See, in this case, the lower limit of integration 1 divided by n as n tends to infinity is 0. So this will be 0. Right? Now the upper limit 2n, limit 2n beta n divided by n as n tends to infinity is 2. So now 2 becomes there. Right? And obviously very easy to integrate this. This you can write as 0 to 2, 1 by 1 plus x squared, that will give you tan inverse x plus x by 1 plus x squared dx. X runs from 0 to 2, half 2x log mod 1 plus x squared, right? So this is tan inverse x plus half log 1 plus x squared. X runs from 0 to 2. Yes or no? You can then supply the limits to evaluate this limit. Try this limit without this. Try this limit without this too. It's going to be quite a task. It can be done, but it's going to take a toll on you. Right? Got me? Let me also evaluate the next one. Simple. Realize this time it didn't turn out to be 0 to 1. It turned out to be 0 to 2 because limit 2n by n as n tends to infinity is 2. Clear? Right? Now, we have in the next one limit n tending to infinity, n factorial by n to the power n whole to the power 1 by n. Where on earth is the summation here? It's a product. N factorial is 1 into 2 into 3, etc. I don't have a summation, dude. I only have a product here. But, hey, I can convert a product into a sum by taking the logarithm. Then a product gets converted into a sum, yes or no? Right? The product will get converted into a sum if I took the logarithm. Let's take the logarithm. Let me call this y and take log y. Right? Now if I took log y, this is limit n tending to infinity 1 by n log n factorial by n to power n right? N factorial is what? 1 into 2 into 3 up to n, right? So let me write this as 1 into 2 into 3 into n, and there is a n to power n in the denominator, which I can write as n into n into n into n, so that there is a complete pairing with the numerator. So this is like log 1 by n plus log 2 by n plus log 3 by n plus log n by n, right? Yes or no? So it's got converted into a sum. Limit n tending to infinity, 1 by n summation log r by n. R varies from 1 to n. Is it not this? And everything is in place. 1 by n summation f of r by n, r equal to 1 to n. Beautiful. Exactly the way the doctor prescribed, right? 1 by n to be replaced by dx, r by n to be replaced by x, the summation to be replaced by the integral sign. So log x dx, 1 by n as n tends to infinity is 0, n by n as n tends to infinity is 1. All of you by this time, x log x minus x, x runs from 0 to 1, right? When you integrate this by parts, all of you know how to do this, right? ln x, x ln x minus x, x changes from 0 to 1. Now at x equal to 1, it's 0 and this is minus 1. At x equal to 1, this is 0 and this will become minus 1. At x equal to 0, hey, problem now. At x equal to 0, this part becomes 0. But this is undefined at x equal to 0. But if it is undefined at x equal to 0, what you should do is take limit x ln x as x tends to 0. You know, the value of this at x equal to 0, x ln x minus x, should be looked upon as x tends to 0. This will be 0, and I have told you this limit. Limit x ln x as x tends to 0 is how much? 0. Right? We've discussed this time and again. So this is 0. So this simply becomes minus 1 plus 0. That makes it minus 1. Minus 1 minus 0 to be technically right. Right? So then, y is what we are seeking. But what we have got is, yes, please ask me. Huh? किसमें? इसमें right hand ही है, because all quantities are positive ना, x tends to 0. Nothing is negative here, you realize that? Quantities are all positive, so it's okay. When I'm going from x equal to 0 to 1, I don't have any value of x to the left of 0, isn't it? Do I have any value of x? So it's obviously x tends to 0 from the greater than 0 side, because the limit is all in the region to the right of 0, isn't it? So it's fine in this case. Yes, you're right. The left hand limit doesn't even exist, because, right? So minus 1 log y therefore turns out to be minus 1. Y is what we are seeking. Y therefore would be e power minus 1. So 1 by e is what y is. Right? Now, let me tell you some important reduction states. What I mean is, say an integral of the kind sin x to the power n dx, x runs from 0 to pi by 2, where n is a whole number, say n is a whole number, 0, 1, 2, 3, etc. Right? So when I want to obtain, let's say, sin x to power 30, such a huge thing, now that's going to become very cumbersome, you know, converting into multiple, sub-multiple angles and so on and so forth. It's going to get very horrendous if I had to do it ab initio. I mean, sin squared x, all right, half 1 minus cos 2x. Sin power 4x also, I can say half of 1 minus cos 2x whole square and then convert into 4x, etc. I can say sin to power 9x, sine to power 10x. The higher the power, the greater is the issue associated in an agenda that calls for converting into multiple angles, right? Therefore, what we have to do is a brighter way of dealing with bulky powers of n. If I can connect an integral with a higher power of n to an integral with a lower power of n, then I can reduce the state of that integral. That means, suppose this is in, and I can reduce it to I of something less than n. See how we do it. So this I could write as sine x to the power n minus 1 into sine x 0 to pi by 2, right? Just an attempt to reduce it to a lower power. Just an attempt to reduce it to a lower power. Then what I do is, this I integrate by parts. In my attempt to integrate this by parts, I integrate this because this is readily integrable. Integration of this will give me minus cos x, and this is easy to differentiate, right? So I integrated by parts by integrating this and differentiating this, right? So this will be my first function, this will be my second function. First function into integral of second function. So this then becomes sine x to the power n minus 1 into integral of sine x, which is minus cos x, right? 0 to pi by 2 minus integral. This thing would be copied and pasted there, minus cos x. So that will make it plus cos x into derivative of this with respect to x. Derivative of this with respect to x would be n minus 1 sine x to the power n minus 2 into cos x. Into cos x, right? So cos x, that will make this cos squared x dx. X runs from 0 to pi by 2. I hope all of you realize what I've done here. Ordinary integration by parts. First function, second function. First function into integral of second function minus integral of second function and derivative of the first function, right? Now, look at this. At x equal to pi by 2, this will become 0. Cos 9. So this whole thing becomes 0. At x equal to 0, this will become 0. So this whole thing. So the first part is 0 anyways. This one turns out to be 0 when I supply the limits, right? The second part is n minus 1 integral sine x to the power n minus 2, and this cos squared x I can write as 1 minus sine squared x. Yes or no? Now this into 1 will be integral of sine x to power n minus 2, which would then be referred to as in minus 2. That will be referred to as in minus 2. So this then becomes n minus 1 in minus 2, and then sine x to power n minus 2 into sine squared x will give me sine x to power n, which is in. So minus in is what you get, right? The whole thing then is in, right? This in can be transposed on this side. So 1 plus n minus 1, that makes it n. So then we end up getting if I transpose this n on this side, I get n is n minus 1 in minus 2 is what I get. Yes or no? That means, say if I had knowledge of sine x to power 8 0 to pi by 2, then I could readily obtain from this formula integral sine x to power 10 0 to pi by 2, isn't it? Suppose I had knowledge of sine x to power 20, then I could obtain sine x to power 22, 0 to pi by 2, right? So going the other way around, if I had knowledge of sine squared x, then from this I can get sine to power 4x, from which I can get sine to power 6x, then from which I could get sine to power 8x. If I had knowledge of sine x, then from this formula I could get sine cubed x, then sine power 5x, then sine power 7x. Any amount of bulky powers could be obtained with the help of this state, which is called a reduction state. This is called a reduction state. For this integral, this is a reduction state or a reduction formula. Let's see how it goes. This one? Okay. See, what I did here was, I could write this as n minus 1, this into 1, integral sine x to the power n minus 2 dx, 0 to pi by 2, right? And this into this is sine x to the power n, so minus integral 0 to pi by 2 sine x to the power n dx. This then is in minus 2. If this is in, this would be in minus 2, this would be in. And this in I transposed on the left hand side, which is all in. The left hand side is in. To get this. Got me? Yes. No, of course not. Because if you did that, realize that this part will not become 0 in an indefinite integral. It's only after I supply this limit that the first part has become 0. So we cannot use that, right? Now let me get a general, using this formula, using this reduction formula, let me get in entirely in terms of n. See, eventually I want in in terms of, if I want I20, integral sine x to the power 20, I want to be able to know in terms of n equal to 20, integral sine x to the power 20, 0 to pi by 2, right? So we need to package it slightly more. Let's package it a little more, right? Now, no big deal, because I of n in this case is n minus 1 by n, I n minus 2. How about it? Right? This is the subscript in this case. What it means is I of London is London minus 1 by London, I London minus 2. That's how you want to read it? So now this is my new I London, right? I can use the same formula. So n minus 1 by n. I of London is London minus 1. That means now it will become n minus 3 by n minus 2 into I London minus 2. That means I n minus 4. Right? Yes or no? You realize what I've done here? No? Sure, no? I can go down further. What I can do is, I could write this as n minus 1 into n minus 3 by n into n minus 2. I London would be London minus 1, so n minus 5 by n minus 4 into I n minus 6. Right? Isn't it? Huh? Go down further. N minus 1 into n minus 3 into n minus 5. Now, divided by n into n minus 2 into n minus 4. I London would be London minus 1. That means n minus 7 divided by n minus 6 into I n minus 8. I can keep. See, the bulk here is reducing, isn't it? see how things are happening here is, so this is in, you can keep going this way, right? Now n could be even or odd. See, the parity is important here. How? N minus 1, n minus 3, n minus 5, n minus 7 will either be all even or all odd. If n is odd, for example, they will all be even. If n is even, all will be odd. Look at this similarly, because they all differ by 2. If two numbers differ by 2, then they would either be both even or both odd. Same with the denominator. n minus 2, n minus 4, n minus 6. They have the same parity. Either all will be even or all will be odd, depending on the parity of n. Right? Now, if I keep reducing the bulk, realize that this term in minus 8, in minus 2, n minus 4, n minus 6, n minus 8, they will also have the same parity in terms of their subscripts, because they differ by 2. That means if I keep producing this chain, then the last member of the chain will either be I0 or will be I1. If n is even, then it'll end with I0. The chain will end with I0. If n is odd, the chain will end with I1. Yes or no? You know what I'm saying? Depending on the parity of n, this chain will either end with I0 if n is even, or will end with I1 if n is odd. Clear? So, let me formalize this chain a little further. So far so good, right? In is n minus 1 into n minus 3 into n minus 5 into, say n is even, say when n is even. Alright, n is even, n minus 1, n minus 3, n minus 5, n minus 7. See, when n is even, n minus 1, n minus 3, n minus 5 are all odd. Yes, so this chain will end with 1. This chain will end with 1. Okay, the denominator. When n is even, n minus 2, n minus 4, n minus 6 are all even. So, n into n minus 2 into n minus 4 into n minus 6, they are all even. And realize that this chain then will end with 2. 2. When n is even, this chain will end with 2. See? Right? And this will become I0. This will become I0. Hey, now I0 is easy to obtain. If you put n equal to 0, it will become pi by 2. I0 will be pi by 2. Do you see that? I0 is pi by 2. Put n equal to 0. Put n equal to 0, integral dx 0 to pi by 2, that's pi by 2. Isn't it? So when n is even, this is the formula for in. If you use this formula, I100 or I200 or I500 is just, with the help of this you can use. Put n equal to 200 or 500 or 6000. Just use this formula. Clear? Right? Say when n is odd. I want you to remember this result. Now then in, realize then if n is odd, n minus 1, n minus 3, n minus 5, n minus 7 will all be even. The chain will end with 2. The chain will end with 2 when n is even odd, right? So n minus 1 into n minus 3 into n minus 5 up to 2. Look at the denominators. N is odd, so this odd, this is odd, this is odd, this is odd, this is odd. And this chain, see, the last member or in the denominator is always one more than the numerator. So if this is 2, the last member here will be 3. One more than the numerator, isn't it? one more than the numerator. So it will be 3, isn't it? So I get like a n minus 2, n minus 4, up to 3, and instead of ending with I0, it will end with I1, and I1, as you can see, is only integral sine x dx 0 to pi by 2, which is simply 1. I1 is 1. Right? So when n is even, this is the result. When n is odd, this is the result. For integral sine x to power n, 0 to pi by 2. Right? And for sure, this also is the same as integral cos x dx 0 to pi by 2. Why? Integral fx dx 0 to a is f of a minus x dx. So sine 90 minus x, that will make it cos x to power n dx 0 to pi by 2. Right? So the same result for cos x to power n 0 to pi by 2. Same result. A must remember result. Right? Now, another important result which I have to equip you with. Let me know if you're done with this and I can wipe this off. Right? M and n are natural numbers. M and n are natural numbers, and I want to be able to deal with an integral of the kind I m n x to power m 1 minus x power n dx. X runs from 0 to 1. X runs from 0 to 1. I want to be able to deal with this. M and n are natural numbers. Integral x power m 1 minus x power n dx. Right? The first thing that I do is integrate by parts. Alright. Say, it does not matter in this case which one I integrate, which one I differentiate. Let's say I integrate this and I differentiate this. That means this will be my first function, this will be my second function. First function into integral of this function, etc. Right? So I m n is one minus x power n. Integral of x power m is this. X runs from 0 to 1 minus 1 by m plus 1 differentiating this with respect to x, chain rule, 0 to 1 is what I get. Isn't it? Got me? Now, at x equal to 0, this part becomes 0, so this whole thing will be 0. At x equal to 1, this will become 0, so the whole thing will be 1. So this integral essentially goes into oblivion, right? So I am left with just this. So this is 0, leading to I m n as n by m plus 1. Now, if this is I m n, this form is the same as this form, except that instead of m you have m plus 1, instead of n you have n minus 1, isn't it? So if this is I m n, what should I call this? I m plus 1, n minus 1. Very good. Yes or no? This will be my reduction formula or reduction state for an integral of this kind. Let's see how we could exploit this further. Let's try and exploit this further. Right? Can I wipe this off? IMN. Right. Okay. This I can write as n by m plus 1. See, I of London Patna is Patna by London plus 1, I, London plus 1, Patna minus 1 is what I have, isn't it? That's E state. So this is also I, London Patna, right? So this is as good as saying this numerator, n comes here, in this case n minus 1 will come in the numerator, and this will increase by 1, m plus 2, and this will become I. These are increasing by 1 and these are decreasing by 1. So this is m plus 2, n minus 2. Right? Again apply the same reduction state to I m plus 2 n minus 2. This is going to become n into n minus 1, and 1 less than this, n minus I'm sorry, same n minus 2 divided by m plus 1 into m plus 2, and 1 more than this, see, 1 more than this, so it will become m plus 3, I m plus 3, n minus 3. Yes or no? Huh? Now in this whole scheme, these are increasing, these are decreasing, right? This will at some point will become n minus 1, n minus 2, n minus 3, n minus n will become 0. When this becomes n minus n, which is 0, this will become m plus n. And that's good because this part will become 0, very good for us, right? So eventually if I keep reducing it, then I end up getting, say, n into n minus 1 into n minus 2 going this way. Let me write this first, I m plus n comma 0, right? Now eventually realize that this is m plus n comma 0. This one is 1 more than this, the last member of this chain. So when this is 0, this last member of this chain will become 1. Yes or no? Right? Okay. Then the denominators. M plus 1 into m plus 2 into m plus 3. Now, realize that at all times, this is going along with this. So if this is m plus n, the last member of this link would be m plus n. Right now? Sounds good? Now, the whole task is then to find I m plus n 0. Then our problem is solved. Right? I m plus n 0 means what? Replace m by m plus n and n by 0. So, I m plus n comma 0 is only this. X power m plus n. Put n equal to 0. Dx, x runs from 0 to 1. That's what it is. I m plus n comma 0, which is 1 by m plus n plus 1. Right? So let me replace this with 1 by m plus n plus 1. Yes or no? Right? Now the numerator is good, n factorial. The denominator can also be made good. I multiply it with m factorial. I multiply the numerator also with m factorial. Right? So then this will become 1 into 2 into 3 into m plus 1 into m plus 2 up to m plus n plus 1 is m plus n plus 1 factorial is what becomes of the denominator. Right? So this imn is m factorial into n factorial divided by m plus n plus 1 factorial. And hey, funny thing, but not so funny. You can interchange m and n and nothing changes here. And no surprise, because look, 0 to a fx dx, x can be replaced by 1 minus x here. So replacing x by 1 minus x to power m into replacing x by 1 minus x, this is x power n, which is I n comma m. So if an expression of imn emerged, in that m and n should necessarily have been interchangeable, as you can see. Right? So if someone gave you like x power 30 into 1 minus x power 40 dx, x runs from 0 to 1, then you know, so easy, 30 factorial into 40 factorial divided by 71 factorial, right? Evaluating this could be another issue, but leave it here. A junior can do it for you. Got me? Of course, you know, there are special techniques of approximating factorials. When factorials are very huge, you know, we have what's called the Stirling's formula for reducing the factorial. Those are approximations to factorials that we deploy in engineering practices. But for this magnitude, the exact value could be evaluated. But sometimes you can leave it at this. You don't have to dig down to that huge 400 digit number, right? You can reduce it. You won't have space to write so much. So this is again a result to remember. You have to remember this result. Okay. Another quick one. In tan x to power n dx 0 to pi by 4 this I could write as 0 to pi by 4 tan x to power n minus 2 into tan squared x, but tan squared x could be written as sec squared x minus 1 dx, right, which is to say 0 to pi by 4 tan x to power n minus 2 into sec squared x dx minus tan x to power n minus 2 dx 0 to pi by 4. This is function raised to a certain power into the derivative of the function. Tan x to power n minus 1 by n minus 1 0 to pi by 4. And this is I n minus 2. This is I n minus 2. I n. I transpose I n minus 2 on the left hand side. So I get I n plus I n minus 2. Yes. At x equal to pi by 4, it's 1. At x equal to 0, it's 0. So that makes it 1 by n minus 1. Another result which you want to remember. We don't reduce it any further. This could sometimes be handy. See, there are many more reduction states, but I don't want to overload you with reduction states. Stay put with whatever I've told you. That should suffice. Alright, otherwise, you'll get messed up. Your hard disk will get clogged. Okay, let's not do that. Start working on the problems from the sheet. We'll join you in a little while.